Hi everyone. So now we're going to move on to Griffiths 9.2, where we're going to actually apply the Feynman rules for quantum chromodynamics. Okay, and we're going to start off with the simplest version first. Just a reminder, right? The way that Griffiths draw his Feynman diagram is that he's going to have time moving in the vertical direction, and then it's basically some sort of distance in the horizontal. So every time Griffiths gives a Feynman diagram, I'm going to rotate it so that we are more used to the Thomson rotation of the Feynman diagram. So just make sure I do that, otherwise it'll be a little bit confusing. Okay. What we're going to do is that we're going to rotate this little diagram so that time goes horizontal and then space goes vertical, right? So this is a quark anti-quark scattering, meaning you have a quark coming in, quark number one, right? And then it exchange a gluon with another quark, right? Let's call this quark one, quark two, and this will have some momentum P1, P1, P2, oops, right? And this also has some color one, color two. Right, now we have to keep track of not just the momentum, the helicity, but also the color. Okay, and then the quark scatters off, right, and it will have some momentum P3, and then the color can also change. Okay, because when you exchange a gluon, you actually can change colors. Okay, this will have some C3. So let's have the particle arrows, right? Okay, and then we have our outgoing quark, which also has a different momentum and also a different color. Okay, all right. So remember, this is time and this is space. Okay. All right. So I listed all the Feynman rules down here. So let's see if we can do this. Oops, it always goes blank for some reason for a second. Okay. Actually, what I should do is actually move this down here so I can actually see the same version of it, right? The one we're used to. Draw the lasso thing, grab it, okay, and then move it down, move it down, move it down. Oops. So the mouse, so we can move it down, down, okay, move it down. Let's delete this one because usually that's going to be more confusing than it needs to be. So let's do that. Okay. All right. So this is the diagram we're dealing with. Okay. So just like QED, right? What we do is we start off going backward following these particle lines. So I'm going to do P3 first, right? So the matrix element I squiggly M, right? We start off with, this is a particle, okay? So this is the quark and this is the anti-quark. I'll even put little bars on top of it just to make sure to remember that. Okay. So that's a particle, but then as a particle, you put the adjoint, right, of that. Okay. And the Feynman rules is that, let's go up here, right? Not only do you put this, but you also have to have this color factor in front of it. Okay. So this will be U of P3, right? The color 3, whatever that happens to be, is that an upper index or lower index? Okay. It doesn't actually tell you. Okay. In this case, since we're on the left-hand side, we also have to dagger it so that we actually have a row vector instead of a column vector. Okay. Now we're at the vertex. How do we deal with the vertex? Since this is a gluon vertex, quark gluon vertex, we write a factor of this, I G S over 2 lambda alpha gamma mu. Okay. Right. The next thing we see here, right, is going to be this incoming quark, right? Since it's an incoming quark, we just have U of P1, okay? And then whatever color of that quark 1. All right, so be a little careful, right? So one thing to notice is that we're going to have the spinner stuff being multiplied by these gamma matrices, right? Those are 4x4 vectors, and then 4 component vectors, right? And then you have this gamma matrices that rotate things, and then when you squish them together, basically all the stuff in blue is going to turn into a number, right? Similarly, right, you have this color thing, right, where you have 3 component vectors, and then you have a 3x3 matrix. You multiply all those together, that also turns into a number. Okay, so that's the idea. At the end of this, we need a number, right? Okay. All right, so let's keep going. So that's one of the vertex. Okay. All right, so there's this gluon being exchanged between them. So that's the propagator. Since this is a gluon propagator, we can use this negative I G mu nu delta alpha beta. Okay, delta alpha beta, right? What it tells you is that it's basically a matrix where is the components are 1 unless alpha and beta, alpha equals beta, everything is equal to 0. Okay, and then I think there's a q square on the bottom here, right? Yep. Okay. All right, that's the other part. Okay. I'm gonna not go off on the right hand side of the screen here. Actually, maybe I do have space. Let's do that. Okay. So now I deal with the other particle, right? Now that we're dealing with the anti-quark, right? So the anti-quark, right? Instead of going backward, we're going backward. Oh, I drew these arrows wrong, didn't I? So since you have an incoming anti-quark, right? You draw the particle lines arrows backward, right? Because those arrows are actually tracking the particleness of things. Okay, since we have an anti-quark, right, instead of the particle spinners, we have to deal with the anti-particle spinner, and specifically, we're going to have to use this one, whereas P2, because we're going backward along the particle line. Okay, and then we reach the vertex once again. This is the same vertex, right? We just have this IGS, okay? And since we already use alpha and mu before here, right, we have to use a different Greek letter, right? And therefore, this is going to be lambda beta and then gamma mu, okay? And then all that divided by 2, okay? Whew, almost there. Okay, ooh, forgot one important thing, right? We forgot the color factor. Okay, that's P2 adjoint, right? Still be C2 dagger here. Okay, and then when we go back, right, to this outgoing quark, that's the particleness is going outgoing anti-quark, so you have a particleness going into the vertex, right? That's going to be V of P4, right? And then you still also have the color factor for C4. Right, so that's what we get by applying the Feynman rules, and if we compare that to exactly what Griffiths wrote down, so hopefully we can see everything, right? So Griffiths have the shorthand where instead of saying P3, he just writes 3. That's okay, right? Hopefully that's understood. But what we're going to do is going to rearrange things a little bit, okay? Because, right, these GS's, 2 GS's, these I's, right, they're numbers, so we can actually move them out in front, okay? So what's going to happen is that, and I'm also going to cancel out, right, this IM with this negative I with this negative I, so therefore we're going to have to carry that around. Let's just do this in red, okay? So I'm going to so multiplying negative I to negative I, you get -1, right? And then you got 2 factors of GS's, GS square, right? And then these factors are 2, right? Multiplies to 4. What else is a number? The Q square is also a number, so we can actually bring that back here. Okay. The rest are these complicated matrices and stuff like that. But what I'm going to do is I'm going to put the 4x4 stuff, the spinner stuff, in one part, and then the color stuff in the other part. Okay. All right. So let's deal with the spinner stuff first, right? So I'm going to highlight the spinner stuff in green, right? So this is the 4-component spinner. That's the 4x4 matrix. Okay. I'm going to bring that out. Okay. That's going to be U bar P3 gamma mu. Okay. U of P1. Okay. Right. Right. And then the other spinner stuff, right, is down here, V2, V4, and then this gamma nu, right? Okay. What's going to happen is that, right, since this is a new upstairs, when we multiply that to this gamma mu, it's going to bring that mu upstairs. It's going to multiply the mu upstairs downstairs. It's going to actually bring the mu downstairs. Okay. So this will be V of P2, right? So this gamma mu times G mu nu, right, is going to give us a gamma mu downstairs instead. Okay. And then we also still have the P4 at the end, right? P4. Okay. So that's all the QED stuff, the 4x4 stuff. Okay. Now I'm going to put the color stuff on the other part. Okay. Right. So let's highlight that in blue. So this is the color thing. This is the color thing. And then remember, these lambda matrices are the 3x3 matrices that actually multiplies to these color factors. Okay, there's the one, there's over here. So I'm going to collect those together. Okay, C3 dagger, lambda alpha. Okay, and then C1 without the dagger. And then now you have this delta alpha beta thing. Okay, what that's going to do, right, it's going to basically multiply to this lambda matrices, right? And it's basically going to change everything. That it basically changes the lambda matrix from having a beta upstairs to an alpha downstairs, just like before. Okay. Let's see what I'm going to do here. Okay, so we still have C2 dagger, right? And then you're going to have, well, the way that Griffiths writes this, he just leaves it upstairs, so that's okay. Okay, and C4. Okay, so in Thompson, okay, right, we find so that's the result that that Griffiths also have. Okay, in Thompson, right, so what we have, we're going to just compare this to quantum electrodynamics and see that these color factors is the only thing that changes. Okay, all right, so what we see from Thompson is that when you calculate the matrix elements for, let's say, electron and tau scattering off each other, right? Same looking process, but instead of, quarks, you have charged leptons. Okay. What we can see is that, right, this piece here is exactly the same as this piece here. Okay. This piece here is exactly the same with this G mu nu, right? This piece here. So all the spinner stuff are the same. You even have this Q square stuff on the bottom, right? These electron works as the coupling constant, right? So these are exactly the same, except for this factor of, well, let me highlight this in a different color. Let's do that in yellow, right? 1/4, right, times these color vectors and lambda matrices, the Kalman matrices, okay? Right, so this is where we want to actually calculate what that is, right? So we're just going to bring that down here, okay? And okay, so to calculate these color factor, we actually have to specify the color of the quarks. So let's just do well, we're going to do example 9.1 in Griffiths, but the idea is that, maybe we have some quark coming in, right? Oops, and then spits off of gluon, and then you have a quark coming out, right? And then we have an anti-quark coming in, right? And then let's say, this top one is red, so therefore, so this is the one with P1, and this is with P3, and, since this quark has to carry away that color, that's going up, outgoing quark also will be red. And then P2 here, right, that's the antiparticle. Let's say this has the color of B bar, the opposite of blue. And then P4 will have the color of B bar to carry away, just so that we have color conservation of incoming outgoing particles. Okay, so let's calculate what this color factor is up here, right? This one for C3 lambda C1, C2, lambda, C4. Complicated matrices, okay? All right, so since we define these colors to be, the incoming quark and the outgoing quark to be red, so therefore the 3-component color matrix, color vector, right, is going to be have 1 on the first component. You remember that the second component represents blue, the third component represents red, right? Since this is an antiparticle, the antiparticle actually negates this blue bar stuff. So therefore, the colorness of the antiquark is actually going to be 1 down here in the middle component. Okay. Okay. So now we get to compute this color factor, right? Remember this dagger here? Change it into a row vector. And then you still have the column vectors here. And this lambda alpha, right, is one of the 8 possible Gell-Mann lambda matrices. Okay. Similarly, for the antiquark, you have the other side, right, C2 and C4, right? You have this row vector, you have this column vector, but instead of having the components in the first part, you have the component on the second part. So when you do these multiplication, what's going to happen is that since this row vector only has stuff in row 1, column 1, it's going to pick out what the component that are non-zero, right, on these Gell-Mann matrices, only if their component is the component of 1, 1 not being non-zero. Okay, but because essentially what you need to do is just add them all up, right? You're going to add up, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, because this actually alpha thing implies a summation sign between them. Okay, but it's going to turn out we don't have to do that. Okay, but these components here, right, allows you to pick out, only during these multiplication, we're only going to multiply by 2 into the first row, first column of these lambda matrices in the left-hand side here. On the right-hand side, since these components are only non-zero, and the second part, we're only going to multiply to the second component, second row, second column of these Gell-Mann matrices. Okay, so I pasted the Gell-Mann matrices down here because Griffiths just somehow magically thinks that you're going to memorize all this, but you won't. Okay, so we're going to stare at these Gell-Mann matrices, right? So Gell-Mann matrix 1 is actually not going to be relevant because it has both the 1, 1 and the 2, 2 components are both 0. Number 2 is also not relevant. Same argument here. 3, that's when you have something important. Okay, so therefore, right here you're going to have 1/4, right? We're going to add, right, 1, right, and then times -1. Okay, because that's the this is for when we have 3. All right. Okay. Then we're going to get next. This is also put 0. This is also 0. This is also 0. This is also 0. And now we have another one that's not 0. Okay, so this will add, well, we have its 1 over square root of 3 in front first, okay, and then the first component times the second, the 1 component times the 2 component, right, will give you a 1 here. Okay. All right. So we have this 1/4. This will turn into -1. This will turn into, ooh, forgot about that. Right, since we have 2 copies of this, right, this is actually this squared. Right, this turns into 1/3. Right, just so so this is the 1/1, this is the 2/2 that we multiply by. Okay. All right, so 1 minus 1/3. Minus 1 plus 1/3, right? That's actually -2/3. These cancel out with each other. And then so this color factor actually gives you a factor of -1/6. The negative sign is not going to matter that much, but you do have to keep track of the negative sign when you're multiplying these things together, because we're going to end up squaring these matrix elements anyway. So that's the color factor, right, for one of the possible ways that the different combinations of quarks are going to scatter off each other. Okay. All right. So with that, what I'm going to do is we're going to swap out one of the other case. Okay. Where instead of scattering a quark into an anti-quark, we're going to scatter 2 quarks next to each other. Okay. So this is the Feynman diagram where let's see, I'm trying to remember, right, where he has time going upward, right? I'm going to redraw this Feynman diagram. Okay, so let's do that real quick. Okay, where I'm going to have time going to the right instead. Okay, so we're going to have a quark coming in, right, where it has momentum P1, some color C1. Okay, right, it's going to exchange a gluon. Okay, and then this is another quark, right, P2, different color, right, and then it scatters out. So it's the same, very similar diagram, but instead of the particleness going backward, meaning because you're doing an anti-particle, these are all going to be just particles. Okay, so this will be P3, color number 3. This will be P4, color 4, right? All right, okay. So I'll let you guys figure out the matrix elements for this, okay? The Griffiths basically tells you what it is, but once again, we have another color factor here, right? That's 1/4 times that. This factor is also the same, okay? What happened is that since you have quark instead, right, there are multiple color combinations that would work, okay? In fact, so we just cannot pick anything that has an R bar or a B bar or G bar on it, okay? And those possibilities are these, where you have RB minus BR, and then BG minus GB, GR minus RG, okay? And there's also another set where it's just both RR, BB, and then green, and then you have this thing called the sextet, where you have RB plus BR, and then BG plus GB, and then you have all these different color combinations, RG plus GR plus RG. It doesn't actually matter which combination. Okay, so let's do another example. Right, let's just pick the RR. Right, so that means, right, all of these incoming and outgoing quarks are all going to be red. Okay, that means all the colors are going to be color vectors are going to be all 1 on the top. Okay, if you do this computation, right, what happened is that you multiply these row vectors with these column vectors through this the Gauss matrices, right? What you find is that, well, the only ones that matters is going to be lambda alpha, where the 1 component is not 0, and then once again, since we C2 and C4 are both also red, The only ones that matters is going to be lambda alpha 1 1 also. So these are going to be just multiplied together. Okay. If you go look up what the Gell-Mann matrices are, the only ones that have a non-zero part is once again 3 and 8. Okay. And so what you do is you have these components you pull these numbers from the Gell-Mann matrices, 1 times 1, and then 1/3 square root 1/3 times square root 1/3. So you get 1/3 at the end, and you multiply all this together. What you have is a color factor of 1/3. Okay. For the other configuration, right? So let's say this triplet one. Okay. I think that's what he picked. Yeah. Okay. Similarly, what you do is you basically define, I'm going to define this C1, right? So if this is the red, blue one, okay, this will be, let's say, right, this will be square root 2, 1 over square root 2 up top, 1 over square root 2, 1 over square root 2 for the blue, and then 0 on the other part, and that's going to be the same as the as for C3. Okay. That's what this factors come from, right? Then once again, why are we multiply? Oh, yeah, he just factored out these 1 over square root 2's. Okay, right? So when you multiply these together, what you'll get, right? You get these column vectors, row vectors, multiply them together, and then you also have to subtract the BR version of it. Okay, so that's going to be the other piece where you have these multiplications, and then this just turns into a long algebra problem, and then you add them all up, and you get a color factor of 2/3. So I'll let you guys go through that yourself. Okay, so these are, like really interesting matrix multiplication, but typically, right, since QCD calculations are non-perturbative, meaning that, if you calculate only the first 3, Feynman diagram, you still have infinite numbers to go, right? What's going to happen is that we're going to see a few situations where you can actually utilize these color factor in order to compare them to their electrodynamic counterpart. And we're going to actually see that in the next section. We can actually predict the branching ratio for the hadronic interaction versus the electromagnetic interaction. So we'll see that in the next section here, okay?